Okay, so I want to wrap up this section 5.4 and I want to talk about the net change theorem. So I have this written out here. The net change theorem is the integral from a to b of capital F prime of x dx is equal to f of b minus f of a. This really is it's really the fundamental theorem of calculus, just restated with we're taking the integral of the derivative, and then this is the second fundamental theorem of calculus, because now we are plugging in our limits of integration, our endpoints. So the net change theorem is really just a way of applying the fundamental theorem of calculus too. So I want to look at some examples, and these are examples of situations where you would use the integral to represent like a rate of change. Okay, so that's the main thing here, is that we understand what the derivative represents in context. So if we have a function for volume, we call it v, then v prime of t represents the rate of change of volume. And if we apply this, the net change theorem to the integral from t1 to t2 of v prime of t dt, then we're going to take the volume formula that we get by integrating the change in volume expression. So we are going to put in v of t2 minus v of t1, and we'll get what is the net change in volume between T1 and T2. Okay, so it should make sense. It should make sense that when we integrate the rate of change, that we then get the change in volume from one point to another. So another example, if dn dt, for instance, is the rate of growth in a population, so the number of people in the population is expressed by n, then we have we have the integral of dn dt. So we basically undo the derivative with the integral, and then we plug in our endpoints. And what we end up with is the net change in population between T1 and T2. Another, and this is probably our most common example, if s of t is our position function, then when we take the derivative, ds dt, or s prime of t, then we get the rate of change in position, which is otherwise known as velocity. So when we take the integral from t1 to t2 of s prime, which again is velocity of s prime of t dt, then we just we evaluate the position at the last endpoint and then subtract the position at the first endpoint, and we get what is the displacement. Again, we could use this language, the net change in position. When we take the integral of the velocity. Okay, now this is different than distance traveled, and it's an important distinction because we're still in one dimension here, because we really just have two variables, and so our variable for position is either a height or it's a horizontal position. And what can happen is that our particle, or whatever it is that we are measuring, it can be moving in a direction, and then it moves in the backwards direction. It gets a negative velocity, and then it continues this distance here. So it's hard to tell the way I wrote it. You have to kind of see what I wrote. So if we go this way, and then maybe at this point we go backwards a little bit, and then we go back, let me go ahead and erase this other one where you can't really see what happened. So we're moving along a line, but I'm imagining that my particle here is starting here, and then it's going for a distance here, and then it goes backwards, and then it goes backwards, and then it goes forward again. And this distance from here to here is the displacement. Okay. But when we talk about the distance traveled, we would want to, let me go ahead and cut this here. I'm going to copy it over. The total distance traveled would actually be this piece plus this piece, which is too long, plus that last piece. This would be the distance traveled. So because this should make sense, that the displacement just tells you, you've got here where you started and here where you ended up. And so the back and forth isn't taken into consideration at all. So for distance traveled, we use the integral from t1 to t2 of the absolute value of the velocity, or s prime. Oops, that's ugly. Okay, so this is important. This is an important thing from this section, is that we make the distinction between distance traveled and displacement. Distance traveled is this right here. So let's see if I'll kill it with the highlighters. Okay, so let's go ahead and do an example, just a quick one. An object moving in a straight line has acceleration. Let's go ahead and do this. A of t equals 2t plus 3 meters per second squared for t between 0 and 3 seconds. The object has initial velocity of -4 meters per second, and so we're being asked to find the velocity and then find the distance traveled. So for part A, the velocity is just going to be the derivative. Just kidding. It's not going to be the derivative of, we're not given the position function, so we have to take the integral. We're going to go from 0 to 3. That's from here. And I wrote 1 somehow. And then we're going to put A of t in here. So 2t plus 3 dt. That's going to give us our velocity. So the integral of 2t will be 2t squared divided by 2, so just t squared, plus 3t. We don't need a constant of integration because we have specific values to plug in. And then we've got, when I plug in the 3, I'm going to have 3 squared plus 3 times 3. And then when I plug in the 0, I'm just going to get 0. So I get 9 plus 9, which is 18. Velocity at time t. I'm just kidding. The velocity at time t, you know what? I think I screwed this up. I wanted this to be, actually it's okay. I just didn't mean to write at time t is what it is. So just find the velocity for this time period here. So let me just kind of add that. Let's find the velocity after 3 seconds, I guess, would be the way to say that. So because we're starting at t equals 0, so after 3 seconds, those first 3 seconds specifically. Because if we're accelerating at a or even if we're accelerating at a constant rate, if we're accelerating, then when is important, because we're not going at a constant velocity, because the acceleration would be 0. Okay, so for the velocity for during this time period, we get 19, and the units are going to be meters per second. So one of the things that kind of happens when we take the integral is that we kind of get rid of that second squared, and it's seconds. So if you play with the units, it should make sense. And then for B, we want to look at the distance traveled. So the distance traveled, our formula is up here, but it's really just going to be the same as before, but with the absolute value. So our distance traveled is equal to the integral from 0 to 3 of the absolute value of 2t plus 3 dt. And we've done a couple of examples of integrals involving absolute value, and we have to look for the vertex. The vertex is where our absolute value equation changes direction. So the vertex is going to happen at t equals negative 3/2. Which, let me think. It's not going to happen in our between 0 and 3, so I think we're okay. Let me do a quick graph here. So at negative 3/2, we're at 0. Is that right? Yeah, and then we have a slope of 2. So let's see, up 2 over 1. This is roughly what our y equals absolute value of 2t plus 3 looks like. And here's the thing, between where we care about is between 0 to 3. And our function actually doesn't change there, so we don't have to change anything. So our distance traveled here, we don't need to break it up into two integrals because the vertex doesn't happen in between 0 and 3. So what we get is just the integral from 0 to 3 of 2t plus 3 dt, which is the same thing that we did before. So we get t squared plus 3t. This time, you know what, I need to... This can't be the same thing, and I probably have to start this stupid thing over. I'm not going to, though, because I'm almost finished here. I'm going to cross out the limits of integration here. Okay. And I'm going to, because I need to put plus v naught, because this right here, let me back up just so that I'm super clear here. Okay, so this gives us a limit of a constant of integration. And the reason that I'm doing that is because I was given an initial velocity. And so I need to put this initial velocity into this here, into my distance traveled. So why am I all screwed up here? The distance actually, I think we're okay. We just, that's the problem. The main problem is that we have to put in the limits after we deal, because this isn't, no, that doesn't make sense either. So I feel like abandoning this, but I think, let me see if I get that right. I think I'm okay. No, I'm most definitely not okay. So here's what I did wrong. And luckily I figured this out because I really, really don't want to redo a whole new section. But what I did is I didn't put V in here. If you notice, I put A. So I am showing you by bad example what not to do, which is why I got confused, because I know that I knew that I needed to have like a constant of integration involved here somewhere. So let's cross this out. Whoops, I didn't mean to erase it. I don't want to be too dishonest here, but my distance traveled I had set up incorrectly. So I needed to do the integral from 0 to 3 of the absolute value of V, which is here, t squared plus 3t plus v naught, my initial velocity. If we look at the original question, that initial velocity is -4 coming right here. Okay, now this one, when we look at the absolute value, we need to look at the graph. So that's our t. And t squared plus 3t minus 4 factors t plus 4t minus 1. So I have zeros at -4 and at +1. The -4 we're not going to care about because it's outside of our 0 to 3. So we've got a 0 at -4, a 0 at 1. This is a parabola that opens up. I don't really need to scale the y-axis because I know what's going to happen is that my parabola would be doing this, right? But since it's absolute value, then this is going to get reflected up. So really the thing that I just drew should mirror the dashed bottom part of the parabola, but it doesn't matter because what we're doing this for is to figure out where the breaking point is. So that means that we're going to have to split up our integral up here into 2 pieces because of this one right here. So we have to split up our integral from 0 to 1, and then the other piece is going to go from 1 to 3. The 1 to 3 part is just going to be the t squared plus 3t minus 4 dt. And then the 0 to 1 part needs to be that reflected piece, which is really just going to be the opposite of t squared plus 3t minus 4 dt. Then what we have is, so remember, let's see. The velocity, that was the thing, is you're using the integral velocity to find the distance traveled. And so hopefully that clarifies things, and hopefully it will make you more careful when you're doing things. Don't be like me. Okay. So we've got -t squared, so the integral. So that's going to be -1/3 t cubed minus 3/2 t squared plus 4t. We don't need the plus c because of the limits of integration. When we plug them in, the c would go away. Plus 1/3 t squared plus 3/2 t, hold on, 1/3 t cubed. And this is t squared minus 4t, evaluated from 1 to 3. And then I'll go ahead and show you. We can plug in the 1 to everything and then plug in the 0 here. So we have the 0, because it is polynomial, the 0 will in fact be all zeros. So we just get the coefficients here, and my equals looks like a less than or equal to. So let's make it equals. We've got -1/3 times 1 cubed minus 3 halves times 1 plus 4. And then when we plug in 0, we get 0. So then when we have this, when we plug in the, so here I'm going to show you just kind of a slightly different order to go in. So normally I plug in the top number, plug in the 3 to all the terms, and then plug in the 1. I'm going to plug in the 3 and then the 1 in each term. I'm just going to put that there's an alternate order here so you know that. Okay, so I'm going to do 1/3, and then I'm going to do 3 cubed minus 1 cubed plus 3 halves, 3 squared minus 1 squared minus 4, 3 minus 1. So instead of plugging in the 3 into all the things and then plugging in the 1, I'm basically doing the 3 then the 1 individually in each term. Because of the commutative property, I'm allowed to do that. I can add in any order that I like, so it will all work out. And then I need to simplify this thing, and I'm probably just going to push, let's see, I can do this. -1/3 minus 3 halves, so that is -2/6 minus 9/6, so minus 11/6. But I'm going to use the calculator for the rest of this. 9 minus 1, I'm doing this. It's 27 minus 1, so that'll be 26/3 plus, here I'm going to have 9 minus 1, so that's 8 times 3. Well, 8 divided by 2, so 4 times 3, which is 12, and then minus 4 times 2, which is 8. And then I'm going to put this into the calculator, and hopefully I didn't screw anything up. (89/6). And that is the right answer. So 89/6, I guess we could do, that makes more sense to do an approximation, 14.8. And this was distance traveled, so this was meters. And notice, well, we didn't actually do the we didn't do the displacement, but because we did have to split it up, the displacement would have been a different, smaller number. Okay, this is going to conclude this section, which was 5.4.